Here we go.
Yeah, we do.
Okay.
I got 15,
Okay. Any specific questions on the assignment?
Yeah.
Home. Talk to me.
Number 7.
Is that with the bullet?
Yeah.
No,
No.
on
Talking about the
question.
multiple choice.
Multiple choice.
Number 7.
Which is the weight of an object is directly proportional to A, its mass, B, its inertia, C, the acceleration due to gravity, and D, all of the above.
Okay, look. How do you calculate FG, right?
Mm-hmm. Yeah.
Which is energy.
Yeah.
So right away, you know it's directly proportional to mass.
Yes. Yeah.
Right? Okay? And mass basically is reflective of the amount of inertia of an object.
Okay.
So 1 kilogram mass is going to have more inertia than a paperclip does.
Yeah.
And then it's also directly proportional to the gravitational acceleration.
Yeah.
There you go.
That's what I figured. I just want to check. Just the phrasing inertia kind of threw me off because those.
Yeah, because inertia is completely reflective of the amount of mass.
Yeah.
So if you have more mass, you have more inertia.
Got it. Thank you. Just want to make sure.
There you go. That was simple. Anything else? Yes, Vonda.
Okay, I'm just gonna pick one. I'll do 4.
Number 4.
Yeah.
Is this with the balloon?
No, the 4 on the first half.
Oh, and the question.
Yeah.
Okay? So when jet plane takes off, okay, here's the deal. So let's say here's the jet plane, right? And here's Al in the plane, right? So as he sits here, and let's say the plane's going to take off this way, does Al want to accelerate? Why not? He's at rest. He has mass, therefore he has inertia. So it's like this. When he's sitting here, what if, visualize this, what if the chair that he was sitting in was on a perfectly frictionless surface inside the plane? Okay? The plane would take off, what would Al do? He would just stay right there. The plane would accelerate out from underneath him, right? But he would just stay right there. So what happens is and this is true, like if I'm sitting here and you come up from behind and push me, there's nothing in, here's what's important. When he's sitting here, there's Al, okay, nice hair, right? There's the chair. So there's nothing in front of him pushing him backwards, okay? What he feels is the fact that he wants to remain at rest. So remember, Newton's third law says that for every force there is an equal and opposite force. So the chair is accelerating him forward. He doesn't want to accelerate forward. So when the chair pushes him forward and provides a force, what does he have to do?
Push back.
He has to push back with an equal and opposite force. So there's nothing in front of him pushing him back. He just feels the action-reaction situation where because his body wants to remain at rest. Does that make sense?
Yeah.
Okay. Yeah, there's nothing in front pushing him. He just wants to remain at rest. Okay? Anything else?
There's 100 meters or 100 centimeters per time.
Michael?
Can you do the number 7 question? The problem.
Problem number 7? Is that with the bullet?
Yeah.
Okay, look. There's the gun barrel, right? What's the initial velocity of the bullet? 0. The bullet's at rest. So the bullet's sitting here in the barrel. Do you know the final velocity of the bullet? Yeah. You know the bullet B is traveling at 350 meters per second. Fairly impressive, faster than the speed of sound. So you know V naught, and you know the final velocity. You know the length of the barrel.
Yeah.
You know the distance, right? Was it 24 centimeters?
Yep.
Okay? So, you know an initial velocity and a final velocity and a distance. What can you determine from there?
Accelerate.
You know F equals ma. There you go. Find the acceleration, multiply it by the mass, boom, easy peasy, there you go. Okay? That's it. Yeah. Great.
I had a question on like 10. Yeah, pretty much all of 10. I was like, I kept getting the same values.
Okay, should.
You should, okay.
It's just random, but,
For
so
like
here,
G.
hold on.
Okay.
Okay. Let's talk about kind of all of kin, right? So this is one of the most important concepts that, this is why I wrote this question. So here's a 1/2 kilogram mass, here's a 1 kilogram mass, right? Now, pretend that you don't know the mass, and when you look at this, like you want to figure out how fast it's going after it's fallen. How far does it fall?
Falls like 4.9 meters.
4.9 meters. That's how far it falls?
Yeah.
Okay. So, here's the deal. Do they both start with the same initial velocity?
Yes.
V naught equals 0, right? Now, you know the distance that they're going to fall, right?
Yeah.
Okay. So, pretend that you're back in the acceleration unit, okay? If I say, hey, I'm going to drop an object and it's going to fall 4.9 meters and I want to know how fast it's going. So let's say that it's Gary the golf ball, right? Now, I dropped Gary the golf ball from a height of 4.9 meters. Pretend that you're back in the acceleration unit. Did I tell you that Gary is orange? No. You know why?
It's not needed.
Can you plug the color orange into the equation to calculate final velocity? No, this isn't, V naught, this O doesn't stand for orange, okay? It's not what it stands for. It's initial velocity. I don't tell you that it's a top flight XL1 either. It's not relevant. When we were doing the acceleration unit, did I give you the mass of the golf ball? No. You know why? Doesn't need it. You don't need it. The only thing that's going to determine that final velocity, if you look at V squared equals V naught squared plus 2AX. The only thing that you need is the initial velocity, the final velocity, the acceleration, and the distance. Mass is not a factor. So here's the main point. I got a 0.5 kilogram mass, I got a 1 kilogram mass. Is there more gravitational force acting on the 1 kilogram mass?
Yes.
Yes, there is. You did the calculations. How do you calculate the weight of a 1 kilogram mass? What do you multiply together?
Mass.
1 times
9.8.
9.8 meters per second. So this has a downward force of 9.8 newtons. What's the force acting on a 1/2 kilogram mass?
4.9.
4.9. So here's the first thing I want you to get out of your minds. Exercise this from your minds right now. That the same amount of force acts on everything. It doesn't. If the same amount of gravitational force acted on everything, we wouldn't need the equation mg. We just say it's 5. Okay? It's not. The force, listen to me, the amount of force is proportional to mass. So if you were to draw a chart and put Fg here and put mass here, like if you had a 1 kilogram mass, what would the gravitational force be on a 1 kilogram mass? 9.8 newtons, right? If you had a 1/2 kilogram mass, that would be 4.9 newtons. Guess what? That's a linear function. If you double the mass, guess what? You double the amount of gravitational force. So get out of your minds right now that the same amount of gravitational force acts on everything. It doesn't. It's directly proportional to mass. Now, here's where the magic happens. If you were to find the slope of this line, the slope of this line would be 9.8 meters per second squared. Because if you took like 4.9 and divided it by 1/2 kilogram, you'd get 9.8 meters per second squared. So they end up with the same acceleration, but it's not because the same amount of force acts on it. You have to understand that you have more force acting on more mass so that you end up with the same acceleration. Okay? So do not sit there and go, oh, gravity is the same for everything. No, it's not. Does gravity cause the same acceleration for everything? Yes. But gravity as a force is proportional to the mass. Okay? Now, if I'm going to throw Hank up in the air versus Gary, yeah, Hank's going to take a lot more force to throw up in the air because Hank has a lot more mass. But if they both leave with the same velocity, they're both going to go to the same height, okay? Because look, here was the whole point when I wrote that question, is that you look at v squared equals v naught squared plus 2ax. Mass is not there. So don't confuse the force that it takes to throw something with the acceleration that it has after it leaves your hand. Okay, they're two completely separate things. Okay? Yes, great.
So I was just wondering, like, with the downward force, is it would it be wrong to label it as negative? Since
No, yeah, that's fine.
Okay.
Yeah, that's fine. That's fine.
So on G, they'd go the same height because it's the same velocity.
Yeah, look at the calculations that you just did. What did mass play into the calculations that you did before in terms of that height for velocity?
No, that's why I was.
Yeah. Now, would it take more force to throw the heavier one? Yes, but that's not what we're asking. Okay. Anything else? Honest?
On number 9, I got a really big answer. Is that
Okay.
right?
So let me give you a hint. 6, 7, and 8 should all have answers times 10 to the third.
Yeah.
And your answer to number 9 should be something times 10 to the fifth.
Okay.
Okay?
Okay.
So on number 9, is that the guy that fell, hit the snowbank?
Yeah,
Yeah.
because what I did is I calculated the acceleration using the v squared.
Yeah. So here's the deal. So here's this guy, he falls out of the plane, right? Now, why is he lucky that he lands in a snowbank?
Because it dissipates his energy.
Yeah, okay, it takes him longer to reach a final velocity than if he just goes doink. Okay?
Yeah.
It would actually be more like splat, let's be honest. So here's the deal. So I gave you a bunch of information that you don't need on number 9. Like, you didn't need to know that it was a C-119 transport plane, okay? Really not part of the equation. It was just some background information. So, out of all that information, here's what you need to know. He hits the snowbank going 53.6 meters per second. That's how fast he's going when he hits the snowbank. What's the final velocity at the bottom of the snowbank?
0.
Do you know the distance?
Yes.
Yes. You know the final velocity, the initial velocity, and the distance. You can calculate the,
Acceleration.
and then multiply that by the mass. There's your force. Easy peasy. Don't make this difficult.
Good. I just want to make sure, because like that's a lot of. What is that like equivalent to? All
A
that
lot.
force.
Well, that acceleration is like around 30, so that's like 134 Gs. Yeah, he was very
That's
lucky that he landed flat, so all of that got dissipated out over his body. If he had landed feet first, he would have killed him.
Oh yeah.
Yeah.
So is that like a life tip if you have a fall? So you
Yeah.
don't fall flat? That's
Yeah,
like-
just put
Yeah.
down some snow
Don't
first.
try and land on your feet.
Okay.
Put down some snow first, and then land
Yeah.
on your back.
Make it snow, God, please.
That's
make
what
it
they
snow.
need. Forget about parachutes. Just get some emergency snow. Just open the backpack.
Now, on number 5, okay, here's what you have to understand about number 5. So, we're pushing this thing along at a constant velocity. So, here's what you have to understand, the difference between accelerated motion and constant velocity. If something's at constant velocity, what is the sum of the forces?
0.
Yeah, if you're at constant velocity, that doesn't mean there aren't forces acting on you. It's just that everything adds up to equal to 0. So here's the deal. So I'm pushing along this puck and I stop pushing it. At that point, the forces aren't balanced and you begin to accelerate. So as soon as I stop pushing it, what's going to make the block or cart or whatever it is accelerate?
Friction.
Friction. So here's the deal. So you have to look at these in terms of the context of the problem. So if you look on problem number 4, okay, excuse me, number 5, you're moving with a constant velocity of 5 meters per second. So this velocity time graph is humming along at 5 meters per second. Now, here's what you have to understand. There are only 2 ways that you can maintain constant velocity, and 2 ways only. One is that there's friction and you apply enough force to keep it moving at a constant speed. That's one option. The other option is that you get it moving and there's no forces to impede it. Okay, that's your other option. Okay, that's the only way you can maintain a constant velocity. If there's an opposing force, you apply a force to counter it, or there's just no force at all that causes the acceleration. Because remember, Mother Nature is lazy. So if you get this, like for example, if I'm in deep space, and I take this and I give it a throw, this thing will maintain a constant velocity forever until it interacts some other force which is going to cause that velocity vector to change. Okay? So that's the two ways you can maintain constant velocity. Apply a force to keep it moving, to overcome the friction, or just let it go and there's no forces at all. So, because there was friction that had to be overcome, here's what you want to look at. I'm pushing this thing along for 6 seconds. At the end of that point, I just say, you know, I'm tired of pushing it. So, as soon as I stop pushing it, one of 3 things is going to happen. Either it's going to speed up, it's going to still continue to maintain that constant velocity, or it's going to slow down. Those are the only 3 things that can happen when I stop pushing. So this is this whole Jedi Stofel thing. You stop the force and you watch. As soon as I stop pushing it, Logan, what's this thing going to do? It's going to slow down like this, right? What's the sign of my acceleration? Negative. So here's the deal. When I ask you what's the acceleration, you have to look at these in the context of the problem. Okay? You're moving with positive velocity. You're going to slow down. What sign does your acceleration have to be? Negative. But this is where this requires thought. Because you know mu equals force friction over force normal. You know what mu is, you can find the force normal, therefore you can find the force friction. But this is where you look at this will only produce an absolute value. This equation only produces positive answers. But you have to look at it in the context of the problem. You go, oh, this thing is moving with positive velocity. Perhaps my frictional force is a negative value because that's in the opposite direction. So this will not produce a negative value. It won't. It will not produce a negative value. It's just going to get you a number. But you have to be smart enough, which all of you are, to look at the problem and go, oh, right, this thing has positive velocity. Cool, okay. I'm betting my frictional force is going to be negative because that's in the opposite direction. Okay?
So it would be wrong to, like, I calculated it with just the negative gravitational acceleration, negative 9.8. And so by doing that, it just gives me negative force anyway.
No. You are going down a hole that will lead you to pain and despair. Okay? Just get a number. Okay? Don't worry about positive, don't worry about negative. Just get a number. Then look at the problem and decide if you want to make it positive or negative.
Okay. I
Okay?
guess at first I thought it only applied to mass, but it applies to everything.
Yeah, because this equation is like an absolute value.
Okay.
Because this is a scalar quantity. This is just a ratio. So you can use it to find your force friction, but then decide in the context of the problem, does it make sense to make it a negative number?
Okay.
Okay? We're good. So if all goes well on 5D, that answer should be somewhere in the mid-30s. Because you're already guaranteed 30 meters because you moved it 5 meters per second for 6 seconds. Okay? You're already at 30, so then you're just adding the additional distance that it takes to make something stop. Okay? Okay. Anything else? And by the way, because if 5A is wrong, everything's going to be wrong. Your answer to 5A should be around your current age right now.
It's pretty close.
37.
Would it be,
It actually is.
that's really accurate. Would it be positive?
Okay, so here's the deal. It says coefficient of friction, how much horizontal force must be applied. So I'm not asking for the frictional force. I'm asking how much force is it going to take to keep it moving with a positive velocity. So your answer to 5A is going to be a positive number. Now, if I had said, listen to me, on 5A, if I had said, what's the value of the frictional force that has to be opposed? or overcome, then that answer would be negative, because that's in the opposite direction of your motion. Okay? All right, cool with this. Anything else? Make sure on 5E that you have labeled every part of that graph. Okay, you're going to draw a velocity time graph, and it's going to look something like this when you get done. And make sure that you have labeled everything that I want labeled on that graph. And draw it big enough that I can see it. Some of you are just like all jacked up with how you think I can read numbers and I can't. Also, look at number 2. On problem number 2, how many significant digits are in every answer or every value that I've given you?
3.
3. Guess how many significant digits your answer should have on problem number 2?
3.
3. Let me give you a hint. If you put 4, how many significant digits is that? 1. You are not going to get full credit. And don't, you did it right. No, you didn't. Because if I think of this, I'm thinking you had horrible data. I went through a lot of time to give you good data. Give me good answers. Okay? And by the way, if you have an answer of 0.003, how many significant digits is that? 1. Do these zeros count?
No.
No, they're freshmen. They're taking up space. They don't count. When do you start to count if you have a decimal place? The first non-zero digit, then you count everything to the right. And don't do this, oh, I'll just put zeros on the end. No! You can only do that if it's exactly 0.003. If it's not, you have to give me what these numbers are. So, if you put 0.003, I will flip out, because that only has one significant digit. Not that that might be one of your answers, I'm just saying. What?
Was 9 supposed to be a negative value?
Is the velocity positive?
Yes.
Is he slowing down?
Yes.
So what's the sign of the acceleration?
Negative.
So what's the sign of the force?
Negative. I'll start thinking it out like that.
That's a good idea. That's a good idea. Okay, anything else? Going once, going twice, sold. Get those handed in. While I hand out notes. So, Max.
I wonder if they actually did like the math and the number of points.
Okay.
No, they didn't. That'd be really cool.
Okay. So here's the deal. So if I had to make a list of like the most important topics that you have to really understand coming out of this class, this concept of net forces would be like in the top 3, okay? Because it's so important in terms of how you understand how the whole process of physics works. So what I did is I wrote this story about how net forces kind of works. And so I'm going to read it because you all are horrible at reading. Because if I sent this home to you and said, oh, you all need to read this over the 4-day weekend, you wouldn't, okay? Let's be honest.
Correct.
You'd read what?
I would read it Thursday, Friday, Saturday, and Sunday if that means we didn't have a homework assignment.
Okay, you are going to have a homework assignment to do. Okay, so I'm going to read it in this kind of jacked up Scottish, British / Australian accent, okay, with a little bit of Western twang thrown in. So there's going to be one audience participation section. There's a boo hiss line. Okay.
Oh, I see it.
Yeah.
I see it, yeah.
No, it's everyone.
Oh, everyone.
It's a collective boo hiss. Okay, so here we go. So once upon a time in the kingdom of physician, there were 2 opposing forces. One represented the forward-looking people who wanted progress and were very positive. The other was the faction that opposed everything that the positive people wanted and were generally considered to be negative. Thus in the kingdom there was always a struggle between the 2 forces. Positive people had a variety of tools they applied in their battle. They would push, shove, lift, throw, heave, hurl, and once they discovered mechanized equipment, they started using rocket engines and hot air balloons. Those was viewed as a positive force as they were trying to move the kingdom forward. In opposition to such forward-thinking endeavors, there was the negative people who opposed anything the positive people would attempt, and they were negative.
Yes!
Nice. As with the positive people, they too had various tools at their disposal, but they were limited to only two tools, friction and gravity. The friction and gravity were generally referred to as the opposing forces, as they took away from the endeavors of the forces applied by the positive people. The negative forces could only be used in special circumstances. The positive people were trying to move something horizontally, and the negative people would use friction to oppose the applied force. The more friction there was, the less positive force remained. If the positive people were trying to get something into the air, vertical motion, then the negative people would use the weight calculated by taking mass times your gravitational acceleration. As is true of every epic battle, protocol had to be established to establish who won or lost each battle. After much wailing and gnashing of teeth, it was determined that a mathematical system was to be established that force net equals force applied plus force opposing. Okay, so here's how it all plays out. So let's say that I happen to have a hydrogen-filled balloon, which I do. So if I just let go of it, what's going to happen? Is gravity pulling down on the balloon?
Yes.
Yeah.
Yes. But clearly, the force acting upward has to be greater than gravity pulling down. Now, if I take this same balloon and I put like a little binder clip on it, okay, like so, and then let go of it, does it still accelerate upward?
Yes.
As quickly?
No.
No. Okay? So then I go, all right, well, let me take like a paper clip. Put the paper clip on here, okay? I then let go of it. So what happens to the acceleration then?
Goes down more.
Smaller and smaller and smaller. So there's two ways that that acceleration can become smaller. One is that my buoyant force is becoming less, or my opposing force is getting bigger. So here's how every one of these problems plays out. And the sooner that you embrace this concept, the better off you're going to be. So every problem that you're going to have is going to be based upon this equation. That force net equals force applied plus force opposing. And net force equals mass times acceleration. Now here's what's important. Listen to me very, very carefully. It is only and only and only net force that equals mass times acceleration. That's it. Nothing else. Only net force. Net force also equals the sum of these forces. So here's what we've got with the balloon. Okay? So here's this binder clip, paper clip that's attached to it. So make a sketch to show the forces in which direction that they're acting. If you come up to me and you say, Mr. Burkamp, I don't know how to do number 5. And I will ask you, have you drawn a picture showing all the forces? And if you say no, I'm not going to help you. I'm not doing that to be a jerk. If you don't know what the forces are and which direction that they're acting, you cannot solve the problem. Okay? That's it. I mean, you cannot solve the problem unless you know which direction everything is acting. So, when I take this balloon and I let go of it, clearly, what's one force?
Gravity.
Gravity. Okay, I got gravity pulling down, technically towards the center of the Earth. Now, what do I need to calculate this gravitational force?
The mass of
Mass and
acceleration.
my gravitational acceleration, we got that one figured out, 9.8 meters per second squared. So, if this was the only force acting on the binder clip, if this was the only force, what would the binder clip do?
Go down.
Yeah, that's a neat trick. Oh, it would fall, all right? Because this is the only force acting on it. But this thing is attached to a balloon, okay? Kind of like the movie Up, right? Okay? So we're here, we let go of it, woo, it goes up. So, what do you know about the force from the balloon? Relative to this force?
It's stronger.
Bigger or smaller?
Bigger.
Greater value. And it's going to be pointing upward, right? So that's my fact. So go back to how we started to draw vectors. Here's my first vector. Here's my second vector. Where do you draw the resultant? Ethan. From the origin out. Here's my origin. I'm going to point up like this. So this is going to be my net force. Okay? That's my net force. So as long as that net force points upward, guess what? That's the direction of my acceleration. Simple as that. Now, but here's where the cool thing happens. So, you've got this. If you like vectors, this is a cool way to represent it. So if you know which direction anything accelerates, horizontally, vertically, diagonally, doesn't make any difference. If you know which direction it accelerates, guess what? That's the direction that your net force is going to point. Okay, that's it. Your net force has to point in the direction of the acceleration. There's no exceptions to that whatsoever. Now here's the other thing that you want to begin to do. You want to embrace this idea of setting up a chart where you have FAP and you have FOP and you have FNET. Okay? That's what you want to look at. You want to set up a chart like this where you can list FAP, FOP, FNET. Now, let's just look at this. When I let go, and I'm not worried about numbers for now, we'll deal with numbers later. When I let go of that, what's the sign of my net force? Positive or negative?
Positive.
Positive. Okay, this is going to be some positive number. Generally, we're going to define up as being positive. So what's the sign of my applied force?
Positive.
Positive number, right? Now, what's the sign of my opposing force?
Negative.
Negative number. Now, right away, I know my applied force going up has to be bigger than my negative force acting downward, so therefore I get a positive net force. Now, what would happen if I said, all right, let's say that I know these masses, right? Let's say I know the total mass of the system. Then to actually calculate the acceleration, what I could do is take that force net and divide that by mass to get an acceleration. So at the end of the line, how every force net problem works out at the end of the line is that you're going to try and find an acceleration. Okay? That's what you're trying to find. So if my net force is negative, guess what? What's the sign of my acceleration? Negative. If my net force is positive, guess what? I got a positive net force. Now, here's where the interesting thing happens. Notice that your last step is you divide by mass. Now, I'm going to take this balloon and I'm going to take that binder clip back off of it. Or, excuse me, I'm going to take the paper clip back off of it. Now when I let go of it, what happens to my acceleration? It increases. Now, here's where the magic happens. The net force is still positive. So I haven't changed my applied force. But what did I do by taking off the paper clip?
Your FOB smaller.
I decreased my FOB, right? So the same FAP, smaller FOB. So what's that going to do to my FNET? Make it bigger. So if I take off the paper clip, I have a bigger net force. But here's also where this is important. But if I took off the paper clip, what happened to the mass of the system?
It's smaller.
It became smaller. So not only do I have a bigger net force, I'm dividing by a smaller mass. So that really makes the acceleration go up. Okay? So when you look at the work that NASA did trying to get the Apollo mission to the moon with the Saturn V rocket. Okay? Saturn V rocket was this big monstrosity. And we'll talk about that on Monday. So when you look at trying to launch things vertically, anytime you reduce the mass, you get a double effect. You reduce the opposing force, but then you also have less stuff to accelerate. The less stuff that you have to accelerate, the bigger the net force is, and the bigger the acceleration is going to be. Okay? Key thing. All right. Now, I'm going to put this back on. Okay? Let go of it. Woo! Get close.
Can you make
Now,
it just like still?
make it what?
Is it possible to make it just float in the
Well, that's what I'm going to try and do.
uh,
This might be too much. We'll try it. Oh, that's actually not bad.
oh wow.
It's achieved equilibrium. You know what you're talking about here.
Oh, there you go.
Oh, no, okay, hold on.
Cut off some string, just like a centimeter. Oh, here we go.
We'll see. We'll just have Hold on.
Wow, that's pretty perfect.
That's not bad. A little heavy.
Get some wire
Okay.
cutters and cut the paper.
Now, here's the cool thing, is that if I give this a push up, right? You come back down. But here, if I take this off, it's like you're watching gravity in reverse. So if I pull it down and let go of it, it stops and then goes back up. So it's like a reverse gravitational field. Okay? It's like, oh, that's kind of cool. Now, when I put this back on, let me see if I can take, that's the noise it makes. Took off a little bit of a, whoa, come back. Oh, took off a little bit much. The oxygen will bleed out. Trust me on that one. Oxygen's pretty small relative to the latex and the balloon. So here's what I've got. A little bit of an upward force, right? Okay, not bad. Trust me, probably in about 5 or 10 minutes, this thing is going to start to sink. Because oxygen, even though the latex appears solid, the hydrogen that's inside of there is small. And so what happens when you have these collisions is that the hydrogen actually leaks out of the balloon even though that it appears solid. So eventually I'm going to lose enough hydrogen where that thing will begin to sink. And you think it's solid, but it's really not. So there's hydrogen like diffusing out of that balloon. So like to give you some example, when I did this first block, it easily lifted like this big binder clip. Okay, but in between now and first block, I've lost enough hydrogen that I had to move down to the smaller binder clip because that hydrogen is escaping out. Now, the other way that you can view this is like a helicopter, which I haven't hit. So people ask me, why do you teach physics? Just because I can go to Dr. Botts and go, hey, I need a helicopter. Why? Because I've got to teach net forces. Okay, so I get to buy a helicopter. If I teach math, I don't get to buy one. So we'll give this a go. Okay, now. Yeah, everybody wants one. Now, when that helicopter is just hovering, okay? What do you know about the forces that are acting on the helicopter?
They're equal.
So is gravity still pulling down?
Yeah.
Yes, right?
Wow.
Oh. Ooh.
Ow.
Like, you just crashed into a building, this was your helipad.
Huh?
This was your helipad.
Okay, no, I didn't get that memo, man. Okay? You know, Grape's the one that's got the medical emergency, you
You
know.
didn't even get on the platform.
Okay.
It landed on my head.
Fearless.
Oh, come on.
My bird, I'm bleeding out.
I'm trying.
Oh no!
Can I land it on the... I thought it was farther up. I didn't have my glasses on. Okay.
Blind.
Broken.
Oh, it is not.
Question, how much was that? Where can I get it?
I bought it at Walmart. Whoa. Guys down.
You bought it at Walmart?
Huh? Okay. Problem is, it gets out of range, and then the remote controls don't work because it's like out of range and it doesn't pick up. Signal. Okay. Hours of entertainment pleasure right there. Okay. So let's say that there's our helicopter, right?
Please don't.
And this actually going. Okay.
Oh, that's a good one.
8 years of being bored in physics lectures. Okay, you get good at doodling. All right. So here's the other way that you can view this if you're into like the Godfather series. Okay. So you can think of gravity as being the mafia. Okay. So let's say that the helicopter has a mass of 0.2 kilograms. Okay, let's just say. So if the helicopter has a mass of 0.2 kilograms, what's the gravitational pull acting downward on the helicopter?
1.96.
1.96, because if you take 0.2 times 9.8, you get 1.96. So if this helicopter is going to get off the launch pad, I'll make that negative 1.96 newtons. Okay? So you can think of this as being like the mafia, right? And so if you're going to get the helicopter off the launch pad, you got to pay off the gravity mafia. You got to pay them a $1.96 fee to get the helicopter clearance to take off from the heliopad. Because if you don't pay the mafia, guess what? Your helicopter is not going anywhere. So, which is true of any situation where the mafia is involved, you always have to pay the mafia. Okay? Because if you don't, bad things would happen. Because they come up and, hey, you're a good boy, huh? Right? You're going to pay me my What was that, Max?
Nothing. He wants me to teach you how to talk.
Oh, Matt does good.
I.
He's Italian.
So let's hear that same thing from you, man.
I'm not saying anything. That was Max. That was Max.
Man,
telling me
Max?
that. No,
Okay.
I'm not the Italian one here.
Pizza pie?
You want to be
Please just see if you
Okay.
get it.
So, yeah, you come up like, you good boy, huh? So, now, if I want the helicopter to just hover, I want it to just hover, how much upward force is it going to take?
1.96 newtons.
1.96. So if something's going to hover, I've got to apply an upward force of 1.96 newtons. True? Now, if I want it to accelerate upwards, what do I have to provide?
Greater.
Greater than. So it's like I gotta pay the mafia $1.96. So if I want to actually accelerate upward, I might have to bring like $2.10 to the party, because I'm always going to lose this money to the mafia. Okay, this has to be paid off. The only time, listen to me, the only time you don't have to pay the mafia is if I tell you you are in deep, deep, deep space where the effects of gravity can be neglected or ignored. Okay? Unless you were specifically told that when you go to lift something up in the air, you always have to pay the gravity mafia. Okay? There is no exceptions to that rule. None whatsoever. Now, if I want that thing to land, and it was hovering, what do I want my applied force to be? Bigger or smaller than 1.96?
Small.
Smaller. So then I want some negative acceleration. So basically, here's what's constant when you're flying this helicopter. This number never changes. The only thing that you're doing is you're manipulating the applied force relative to this number. So whenever, listen to me, whenever you have vertical motion in terms of forces, you always have to take into account gravity unless I specifically tell you, don't worry about it. Okay? Gravity is always there. So let's look at another example. So let's say that you get a job for NASA and you're literally like a rocket scientist. Okay? And you've got a rocket and it has a mass of, 1.5 kilograms, let's say. And the engine from the rocket can provide an upward force of 30 newtons. Okay? So this is what you've told. This is how it would play out. Mass of the rocket, 1.5 kilograms. Force from the engines is 30 newtons. And I want you to find the acceleration of the rocket. So what are you going to do?
F equals ma.
You're going to take 30 and divide it by 1.5. So somebody take 30 and divide it by 1.5.
That just 20.
20.
Maybe 20?
Yep.
That'd be nice. I appreciate that.
Everybody cool with that answer?
Yeah.
Not a single person in this room should be cool with this answer. None of you should be cool with this answer. Okay, all of you have obviously never dealt with the mafia. Who did you not pay off?
Gravity.
The Gravity Mafia. Did you take gravity into account?
No.
No. Guess what? They're going to send Guido to find you. Okay? I don't know what Guido's going to do, but Guido is not happy. He has anger issues. Okay? Guido from the Gravity Mafia is going to find you.
Not going to break any.
Now, but I promise you, this is what you're going to do wrong. And I will tell you, there's going to be a problem like this on the test. It will be the bottom on the front page of the forces test. And I'm going to say, here's the force, here's the mass, calculate the acceleration. And you're going to take 30 newtons and you're going to divide it by 1.5 and you go, oh, there's your acceleration. Mr. Burkett, rocket science is not that tough. How difficult is it? You take a force and you divide it by a mass, you get an acceleration. Seriously, what are you so uptight about? I'm so uptight because what did you not take into account?
Gravity.
Gravity. So here's what you do on every problem like this, and the sooner you embrace this idea, the better off you're going to be. You get a problem like this, you draw a chart, and you go fat, fa, finette. Okay? The sooner you embrace this idea, the better off you're going to be. So, when I gave you the 30 newtons, is that 30 newtons my net force, my opposing force, or my applied force?
Applied.
That's 30 newtons. That's my applied force. Because here's where you draw the rocket. Okay? There's the rocket. This is the force that's going up. What do you have to, who do you have to pay off?
The mafia.
The mafia. Guess what? You all tried to cheat the mafia out of their forces. What's going to happen? It's not going to end well. Okay? We're not dead, but Guido's going to come talk to you. Let's get okay? So, yes, Guido. He's going to, let's have the chat. Okay.
So then you
So,
can
you have a mass of 1.5 kilograms. Anytime you have a mass, what can you always find when you have a mass? Find
Force of gravity.
caused by,
Gravity.
Gravity, you can find the weight.
you can find the weight of it, right? Which is the same as a gravitational interaction, right? You can always find that number, always. So if I take 1.5 times 9.8 meters per second squared,
Rodman says he owe him.
why?
He won't let me pay.
Seriously?
Yeah, so he says you owe him.
Okay, I'll take that. Okay.
Buy him a helicopter.
No. Rocket with a helicopter? No. Okay. So if I multiply this by, so somebody take 1.5 times G.
Negative 14.7.
14.7. Now again, just get the number and then decide what you want to do with it. Okay? Just get the number. Don't go, oh, always make it negative. Just get the number. Then decide. Well, here's the deal. If your applied force is defined as a positive value, what's going to be the direction of the gravity mafia? Negative. So I'm going to make this negative 14.7. So out of the $30 that you have to spend, $14.70 of it is spent what?
Paying off the mafia.
Paying off the mafia. So what do you have left over?
It's
$15.30.
too
You've
much
got
math.
$15.30 left over that you get to keep. Now, how are you going to use that to get your acceleration?
Up in the same direction as force applies.
Yes? So how do you take this number to get your
Divided by
acceleration?
mass.
Divide that by 1.5 kilograms. So somebody take 15.5 divided by 1.5.
Wait, wouldn't it be 15.3?
10.2.
It's 15.3. My bad, that's a 3.
So yeah, 10.2.
10.2.
Yes.
You have to do the mass times the gravity.
Now, here's an interesting thing that happens though. Do you think acceleration is a vector quantity?
Yeah.
Think it has magnitude? Think it has a direction?
It does.
Now, here's the other thing that you can do. If you go back here, and we screwed this up, right? and we took the force and divided by the mass and got that acceleration of 20 meters per second squared. What's the value of my gravitational acceleration?
Negative 9.3.
Ah.
did I get here? It just creeped up on me.
Now, so my gravitational acceleration is negative 9.8 meters per second squared. So what's my net acceleration?
10.2.
Which is the exact same answer that you got over here.
Would you prefer this method though?
I prefer this method.
Okay.
Okay, I prefer this method. But it's the same idea. You're going to get the same answer. Okay? Yes?
So 10.2 is the force net.
No.
No, that's accelerated.
That's
15.3 newtons is my net force. Once I divide it by the mass, then I get my acceleration.
okay, and that's what we want.
Yeah, this is the end game here, is the acceleration after you pay off the gravity mafia.
Is that always the same force net, always divided by mass is always acceleration?
Yes, and it is only true of net force. It is only net force that equals mass times acceleration. Okay, now, look at this. So, here's the rocket, looks like Albert Einstein, right? So we fired the engines. At that point, I'm going to shut off the engines, okay? So as soon as I shut off the engines, if you go to this chart, what becomes the value of your applied force?
0.
0. Okay? There is no longer an applied force. What's your net force then?
Negative 14.7.
Then your net force becomes 0 plus a negative 14.7, which should be negative 14.7. You can plug it into your calculators, but I feel pretty solid on that. Now, if I take negative 14.7 newtons, and I divide that by mass of 1.5 kilograms, what acceleration do you think you're going to get?
Negative 9.8.
Negative 9.8, because that's the only force acting on it. Okay?
Fact check you on that one.
Fact checking. Do
Divided
that.
by
1.5.
Negative 9.8, oh wow.
Wow! Who saw that one coming?
I don't know.
Wow. So, here's the deal. This problem works in every situation. Now, what if you launch this rocket with 30 newtons of force, but you're in deep, deep, deep space? What's the value of your opposing force?
0.
What's your net force? 30. Then you take the 30 newtons and divide that by the mass, you get your acceleration, which is going to be 20. So, the only time you don't have to pay the gravity mafia is if I specifically tell you you're in deep space. Otherwise, this has to be taken into account. Now, you go to the moon. G on the moon is like negative 1.7-ish, okay? If you apply the same, the mafia isn't as strong on the moon, okay? So what would happen to the amount of money that you have to apply or pay to the mafia on the moon?
Go down.
It'd be less. So if you have the same applied force with the smaller opposing force, you're going to get a bigger net force. But what's going to happen to the mass of that rocket on the moon?
Nothing.
Nothing, because it's still the same rocket. Okay? Cool with that? Got it. Okay. Now, that's vertical motion. So stand up, take a quick stretch, and we'll deal with horizontal motion.
There we go.
Okay.
Why isn't it sinking? Because the other one isn't on there.
Okay. Are we good?
The other paper
Yeah.
clip.
Okay. Mad Max.
Yeah, it's gone.
Oh, good. So, that's the gravity mafia working vertically. Now, the other branch of the mafia deals with horizontal motion. So, if I give this a push, okay, if I give this a push, what's working against me?
Friction.
Friction. So friction is like horizontal gravity, okay, in the sense that it's going to work against you trying to get you to move. So, let's say that we've got a block with a mass of 1.02 kilograms. And I'm going to apply a force and say 10 newtons, and I tell you that mu has a value of 0.10. So you've got a whole bunch of information here. So here's this block. I'm going to apply a horizontal force of 10 newtons. mass of 1.02 kilograms, mu is 0.1. Now, for now, I want you to pretend that this number isn't here. Okay? You don't know this number. This is number, I've not given you this number. Pretend that it's not here. If I just tell you that I'm applying a force of 10 newtons to a mass of 1.02 kilograms, how can you calculate the acceleration? This is the easiest potential problem I can give you.
Divide by kilogram.
Yes. So I haven't given you coefficient of friction. I haven't given you anything. So if you look at that chart, okay, of fat, finette, you got 10 newtons here. I have not given you any information whatsoever about the opposing force. So for lack of any information about the opposing force, what do you think the opposing force is? Goose egg. So what's my net force? 10 newtons. So once I get that, then how did I get my acceleration? Divide by the mass, boom, there's my acceleration. Easy peasy, right? So somebody take 10 and divide it by 1.02.
9.8.
What'd you get?
9.8.
Now that just randomly worked out that way, okay? It was just completely random. Don't look, oh, it's the acceleration due to gravity. It just was a random thing. Hunter?
So what information do you use to find that opposing?
Now, if I said, here's exhibit B. If I said, hey, mu is 0.10, if I gave you the coefficient of friction, then I would expect you to find the frictional force. Okay? Now, if you know mu, what does mu equal? Mu is a ratio of what two forces?
Fric over.
Force friction over force normal. Oh, how cool is that? Do you have enough information to calculate the normal force?
Yes.
Yes. How?
By multiplying the mass times 9.8.
Beautiful. So if I take 1.02 kilograms and multiply that by 9.8 meters per second squared, which is the acceleration due to gravity, it just happened to work out that it's this number. Okay? Don't think it just randomly worked out that way. Okay? So if I take 1.02 times g, I get 10 newtons. So here's the deal. So if I take mu times force normal, I get force friction. So if I take 0.10 times 10 newtons, I'm going to get 1 newton. So that's my frictional force, right? So here's the setup. I'm applying a horizontal force of 10 newtons. Now my opposing force is going to have a value of what?
1.
Now, do you think I want to make that positive or negative?
Negative.
Negative, because that's going to be going in the opposite direction. So I'm going to make my opposing force, this is going this way at 10, my opposing force is in the opposite direction of -1 newton. So this is the friction mafia. Okay? So how much money do you have to pay to the friction mafia?
$1.
$1. How much money do you have left over? $9. That's your net force. What are you going to do then to get your acceleration?
Take
Divide
that.
that by the mass.
Divide that by the mass, boom, there's your acceleration. Now, what's going to happen to the money that you give to the gravity mafia if this becomes a bigger number? If this becomes 0.2, what's that going to do to the frictional force? Make it go bigger. So, has anybody ever tried to drive their car without completely releasing their parking brake? Okay, what happens?
You don't go very fast. It makes a lot of noises.
Why?
So, pulling this out.
Okay, so you're giving the same applied force, but you've got a big opposing force, right?
For 2 miles.
So then your net is just smoking, right?
It was like for like 2 miles. It was bad.
Yeah.
Oh my
It was just like on there a
god.
little bit. It was weird.
Okay, so if you try and drive with your parking brake on, guess what? You have a big opposing force. What's that going to do to your net force?
Make it small.
Make it smaller. If you've ever seen the commercials of the athletes where they run with a parachute on the back, what's the purpose of the parachute?
To make that force small.
To create
Greater opposing force.
an opposing force. Okay? So then they've got to work harder on the applied force to balance that out. Okay? Got it? Good? Great. Okay, so Mad Max, stop that. Let me head up these signs. Okay, so let me kind of get you through some of these problems. So on number 1, you've got a truck, pretty big, It's traveling at 108 kilometers per hour, and we're going to bring this thing to a stop. Is the truck going to accelerate?
Yes.
Yes. Do you know the initial velocity?
Yes.
Do you know the final velocity?
Yes.
Do you know the distance?
Yes.
Can you calculate acceleration?
Yes.
Does F equal ma?
Yes.
Is what's going to make the truck stop?
Friction.
Friction. So even if you look on problem number 1, and you go, okay, hey, Burkamp, I like your charts, man. It's cool. So I got fat, faux, or if you can just go at fa, faux, whatever you want to do. Okay? And then finette. Is there any applied force to the truck?
No.
No, you're not told that it's being pushed at the same time we're trying to break it. So in problem number 1, there is no applied force. You don't know what the opposing force is. But here's what you do know. You know that net force, and listen to me, net force and net force only equals mass times acceleration. So what you're going to do in problem number 1 is you're going to calculate the acceleration. You're going to multiply that by the mass. That gets you your net force. Well, your net force then has to be the same as your frictional force, because that's what's making it stop. So on number 1, you're in effect going to work backwards. You're going to find your net force, which then is your frictional force because there's no applied force. Okay, so we're not trying to push the truck and stop it at the same time. When you get to question number 3, what are the 2 most important words on question number 3?
Constant velocity.
Constant velocity. All the forces are going to add up to? Zero. Number 4, I tell you an 18 Newton force is applied to a 1.5 kilogram box that's at rest. What's the acceleration of the box? On number 4, did I give you any information about the mafia? No. Number 4 is the easiest problem on the entire assignment. Just use F equals ma. That's all you have to do. That is your net force. You have the mass. Find the acceleration. However, on problem number 5, I become a jerk. So in number 5, notice it's the exact same force. Notice the exact same box. But now I tell you the coefficient of friction is 0.54. So if you know the coefficient of friction is 0.54, Vonda, what are you going to do with that 0.54?
I don't know.
Sure, you just told me when I walked by.
Oh, that's the percent that you pay the mafia.
Yes, the 0.54 is going to tell you what you're going to pay to the mafia, right? So, knowing that number, you know that mu 0.540 equals force friction over force normal. Do you know the mass of the box?
Yes.
Can you find the weight of the box?
Yes.
Yes, then you can multiply that by mu to get your force friction. That's what you have to pay the friction mafia. Okay? Go with this. Now, on number 5, you're going to make 2 diagrams drawn with a ruler, right, Vonda?
Yes.
And you're going to show me the scale. You're going to draw 2 diagrams. One is a free body diagram that's going to look something like this. FG, force normal, fat, and then your frictional force going back this way. With a ruler to a scale. Then you're going to draw this same thing tip to tail. FG, boom, boom, boom. You're not going to end up back at the origin because you have a net force. When you get to number 8, you're launching a rocket. Okay? Now, on this one, I say sketch a free body diagram. This 8 just has to be a sketch. So you got an upward force of 129 newtons. What are you going to have to pay off on number 8? Which mafia? Horizontal or gravity? Gravity. You know the mass, you can figure out the gravity mafia fee. So, then you're going to shut off the engines. Once you shut off the engines, what's the only force left?
Gravity.
What's the acceleration cause when only gravity is left? Negative 9.8 meters per second squared. When you get to the backside, read everything that I want. You have a velocity time graph to draw. Label everything that you have to on this velocity time graph. If your numbers do not fit in this velocity time graph, don't go, well, Burkamp screwed us over. His graph is all wrong. No. Okay? If If you have to add on to the velocity or time, you have done something wrong, okay? Don't go, well, Burkamp's an idiot. Oh. Yeah, speaking of mafia. Okay, all right. So you have 4 days to make this happen, okay? The laws of physics do apply to you. Don't do anything stupid over
He's not gonna make that happen.
the 4 days.
4 days.
All right, Mad Max.
4 days in which you're